My name is Scott Long, and I'm going to talk to you about a project that we've been working on at Netflix to improve high bandwidth TLS encryption inside the FreeBSD kernel. So this talk will be several parts. First part, I'll talk about myself and Netflix, and then Jean-Marc Gurney presented some of our results last year, and I'll go over those as a review. And then I'll talk about what we've been doing in the past year in 2015 to find new areas to improve and what those results were, and then I'll talk about what we're looking at going forward. So about me, like I said, my name is Scott Long. I've been a member of the FreeBSD project for 16 years now. Before that, I actually started using BSD back in 1992, before it was even FreeBSD. And I've been with Netflix for almost 4 years now, and been to various other technology companies since 1999. And I live in Colorado in the United States. So I'm sure that most people should be aware of what Netflix is. It's been available in Japan now for, I think, over a year, and it's available worldwide for several months now. But I do like to talk about it just to give everyone a common ground for later in the talk. So Netflix is a video on-demand company. We started out in 1998 as a DVD by mail company, basically replacing a video store by mail. It was very successful, but it was mostly in the US and Canada, mostly North America. We didn't branch out into other parts of the world. In 2006, we decided that the internet was going to become a thing, that people were actually using it and it could possibly serve video. So we started branching out into online streaming. And when we first did that, we used third-party CDNs. We used Akamai and Limelight and Level 3 to carry our traffic while we built up the infrastructure and decide whether or not it was really going to be something that we wanted to do long term. Now that's grown into a business where we have over 75 million subscribers in 190 countries. In fact, there's very few countries that we don't serve. And in North America, at least, we are 37% of the internet's traffic. So I show this and update it every time I speak. I like doing it, but the part that is Netflix and is FreeBSD gets a little bit bigger every time I show it, which makes me very, very happy. But as you can see, we carry a lot of traffic through our network. It's all running on FreeBSD. The back-end stuff that is like authentication, website, and all that kind of stuff is running on AWS. There was a blog posting about a month ago now from one of our vice presidents about how Netflix had moved all of its data center infrastructure to AWS, and that was absolutely true. Everything that deals with things like encoding or recommendations or the website or payment systems, internal and as well as our internal operations infrastructure is in AWS. However, the part of the company that streams video out is not AWS, that is our OpenConnect network, and that is all running on FreeBSD. So FreeBSD as a video server is actually working very, very well. We're using FreeBSD 10.3 with some modifications and Nginx 1.9. We use a very common Intel server platform. It's based on basically Supermicro motherboards with Intel Xeon CPUs. And we have 3 platforms that we're distributing worldwide to build up our network. Those platforms are basically a chassis that serves a particular purpose. Our first one is what we call a catalog server that has up to 36 spinning drives in it, around 250 terabytes of storage, and 2 10 gigabit NICs for as much as 20 gigabits of serving traffic. And that's really meant to hold large parts of our catalog. We'll put 10 of them together to hold our entire catalog for a certain region, and then we'll stage those around the world to provide access around the world to our whole catalog. Then we have the flash server, which is meant to be a high-performance server, meant to carry the content that's hot and very popular at the moment. That's only about 10 terabytes of storage, but it's all on SSD flash, and In the past, we'd had that on a platform that was 3 10 gig NICs, then we moved to a 1x40 NIC, and now we're experimenting with a 100 gig NIC, and I'll talk a little bit about that in a minute. And then we have our third platform, which is our global platform, which we're just starting to experiment with, and that's meant to go to places around the world that are otherwise underserved with infrastructure or hard to get to, and where we need to keep our costs low. So that has kind of compromised the storage, but very low cost and very low CPU power and connectivity. And that's meant to go to places like Southern Asia and Africa and South America, places where we want to have a presence, but we don't want to spend a whole lot of money doing it. So all these come together to are part of our building blocks, basically, for our OpenConnect network and the all-in FreeBSD. Our network, we're not a pass-through cache. We're not like a SQUID proxy. We stage machines out into various connection points around the world, our internet connection points, where we do peering with other ISPs. If an ISP is big enough to warrant it, we will offer them one or more of our machines for free to put into the network to bring the content closer to their customers. But all these machines are preloaded with content when they go out in the field, and then every night they will stop serving for a period of time. We will do content in that's been determined to be popular for that region, or that's become newly released, delete old content, and then start serving again. So, like I said, everything so far has been up to 40 gigabits of traffic per node. I'm happy to report that in the last few months we can actually serve 100 gigabits of video traffic real time on FreeBSD, single node, single CPU socket. We are really one of the first companies that's actually demonstrated that with 100 gigabits. So I'm really proud of the work that everyone's done there. So, but that's not what I'm here to talk to you guys. I'm here to talk about TLS encryption, what we've done about that. So, why do we care about encryption? Our video is already encrypted with DRM. We have to do that because of our licensing agreements with the movie studios. They don't want people capturing the stream that comes in their computer and then, redistributing it to their friends. It's also a very high CPU computational cost. Most estimates are that when you turn on SSL, HTTPS, TLS encryption, that you've lost half of your CPU cycles just to doing that. So why would we want to do that? If we've already got things encrypted statically, why would we want to start doing TLS? The reason is customer privacy. We believe very strongly in that, and allowing our customers to have a very good experience while they stream. We don't want their ISPs or people working with their ISPs to fingerprint the data that's going through and figure out what they're watching, and then figure out some way to insert ads in or otherwise degrade the experience. So in April 2015, almost a year ago, our CEO made an announcement that we were committed to doing as much HTTPS serving as we possibly can in the coming years. I say as much as we possibly can. We'll never quite get to 100% because there are old devices, old Rokus or smart TVs that don't have the CPU power or don't have memory or whatever in order to do TLS. But everything that's newer, everything that's based on a browser or like on Xbox or PlayStation will be doing HTTPS. And actually already has started doing that. We've already started a migration path of clients to doing HTTPS. So let's talk about the performance impacts of all this. The classical model of web serving is that you have a web server that lives in user land. The data comes from the disk through a read system call, gets copied into user land. User land maybe does something with it, maybe doesn't, and then writes it out to a network socket and goes out the wire. If you were doing encryption with this, it was basically the same thing, but you would do an encryption step while it was in user land. Data gets copied twice. That's not only computationally expensive, although with modern CPUs it's not too expensive, but it consumes bandwidth on the memory bus, and it thrashes the CPU's L1 and L2 caches. You're forcing them to constantly refresh with new data that you don't care about. You're just going to be throwing away right after the operation is done. And pumps out data that could be used in another operation. So, long before we even started doing TLS, we were using the Nginx web server, and one of its innovations was that it was using the sendfile system call to keep all the data movement in the kernel. No data was being copied out to user land. It was using the VM system and the system's RAM as a buffer basically between the disk and the network side. And Nginx was basically just a traffic director. It would get a request in from the client for a certain range of bytes of a certain file, and would just hand it off to send file, and send file would direct that traffic within the kernel. Worked very, very well, worked very well for us. We did improve it by going from a synchronous system call to an asynchronous system call. That allowed us to basically queue up more work at once and allow our CPUs to scale much higher. But then what we talked about last year in our paper, in our presentation, was that we've also added an encryption step to this path. So once again, user land becomes an endpoint for the connections to terminate to and negotiate with and keep state. If your client connects to us via HTTPS, we will do the key exchange and the handshake in user land. But then we will share the key up to the kernel, pair it to the socket, to the file descriptor of the socket that is your network port, and all the encryption will happen in the kernel. We talked about last year that our initial kernel implementation was very, very simple. We used the OpenCrypto framework. The OpenCrypto framework was really meant for things like IPsec, or is meant to be used from user land and give programs access to kernel resources, or maybe kernel drivers that were connected to, that were talking to hardware accelerators. But it was a convenient interface for us to use. Way that we made it all work, though, is we extended the socket interface to accept a socket option that allowed us to share the key into that socket, tell it when or when not to encrypt anything that it couldn't encrypt. Maybe a cipher that I wanted to use wasn't in the kernel. It would fall back to doing it in user land, but for the most part, everything happened in the kernel. One hard part of this was that the original idea was that we would just put the data into the socket buffer and then run an encryption step on it while it was in the socket buffer. Then we realized that for most encryption operations, your data actually grows as it encrypts, because there's usually a hashtag, a verification hash, or a header record of some sort that gets added to the encrypted text. So what may have started on 16K going in your socket buffer actually winds up being 16K plus 20 bytes at the end. So we couldn't put it in the socket buffer and then encrypt it. We actually had to encrypt it on the fly, so it went in the socket buffer. So our results from last year, basically it showed that our approach was feasible, that it worked, but it didn't produce much of a gain in performance. Even though we were no longer copying data in and out of user land in order to do the encryption, we were doing it in the kernel. The gains were very, very minor. But it showed us that we had a starting point, things still worked correctly. There were no big surprises that caused performance to degrade. So we started there, and we kept on working through 2015 and into 2016. And what we did was we looked at 3 big areas for improvement. The first one was that we focused all of our clients to use AES-GCM. This didn't present much of a penalty for them. Computationally, for us on the server side, GCM is much nicer, easier algorithm on the server side because it can be parallelized. It doesn't require 2 passes over the data, one to do the encryption and one to do the hash verification. And it was something that most of our clients could do. So there's, once again, just like there's some clients that will never be able to do encryption at all, there will be some clients that can't do GCM, but as time goes on, those will reduce down to a small enough number. And this helped us because our original testing, we were doing as much as 30% of our traffic with CDC. That was why that wound up actually being a huge performance impact on us. We were spending almost as much CPU power doing 30% CDC and as we were doing 70% GCM. So talked to our client teams, got rid of CDC for the most part, and that helped a little bit. The next thing we did was we started saying, well, we're using OpenCrypto framework and we're using the AES-GCM implementation inside of there. Is that really the best implementation out there, or are there things we can do to make it faster? So we looked, and AES-NI was written mostly in C, had some assembly subroutines for using the AES-NI instructions for doing core parts of the algorithm. But not being crypto experts, we didn't really know what to do with that and how to optimize ourselves. So we started looking for other implementations out there as alternatives. We considered OpenSSL, we considered boring SSL, and we started looking around for other options. So right after that, we kind of discarded OpenSSL because our reading of their APIs was that in order to use their encryption algorithms, they basically wanted to encrypt in place. You gave it a buffer, it would encrypt back into the same buffer and then pass it back to you. Since our source buffer was the virtual memory system of the kernel, we didn't really want to encrypt pages in place because then they could never be used for anyone else. Boring SSL had taken off as a fork from OpenSSL around the time of Heartbleed. We felt that we had better access to the engineers at Google that were working on it. We felt that they were doing a lot more interesting work. And one of the first things that they had done was they had changed the APIs to allow separate source and destination buffers. And they started looking at improving the cipher code for AES, for the various AES implementations. So we started with there, and we did some speed tests. We did some very rudimentary hacking of code into various places, and the results started looking promising. And I'll show the results at the end. But then around August or September of 2015, a bunch of us were in Phoenix, Arizona, talking to Intel about storage and disk drives and that kind of stuff. And a group showed up at the meeting that was part of this team called ISAL. And they started talking about how they had this hand-tuned assembly library that could do encryption, and could do hashing, and could do compression, and that it was all hand-tuned for specific CPU models, and that when it came to things like AES, it could do as much as a 2x improvement over what was in OpenSSL. The funny thing was that they didn't think this was a big deal. They were kind of shrugging their shoulders and say, well, we have this code, but you probably don't want it because no one ever asked for it. So we don't know why we were asked to come up here and talk to you because no one ever wants to talk to us. And meanwhile, everyone around the table's jaws are all dropping, like, yes, please give us the code now. So they were very gracious and gave us the code. It turns out that they're willing to license the code under whatever license we want, BSDL. One hang-up was that it's written in the YASM dialect, not in the, I guess, NASM dialect. But still, that wasn't a big deal, and we started running some initial tests, and sure enough, it was much faster than OpenSSL. It wasn't as much of an improvement over boring SSL, but it was enough to stay interested. And the fact that we had this team of apparently very smart assembly language coders, Alan should point you at them about 16-bit operands, but yeah, so it felt like we had a really good team we could engage with and further improve things on, so we started focusing on ISAL. At this point, we had a bunch of different cipher code that wasn't part of OpenCrypto, was really meant to be run in userland, and we had to figure out a way to start putting it into our kernel stack. Right after that, we realized that OpenCrypto was not going to be fast enough. One of the major problems was that it was single-threaded. Actually, it has a dispatch and return thread, but there's no way to use more than just those two threads. It probably wasn't going to be too much effort to add thread pools and expand it that way. But we were trying to work fast, and we also had this idea that we'd be able to take code from various libraries and modularize it, package it up, and put it into the kernel without any other changes. So, and we didn't feel like the OpenCrypto APIs would allow us to do that. So we started making our own APIs basically to pull in this various bits of library code. One ugly thing is that for using ISAL, it required us to install the YASM port and hack kernel build scripts to call into an external assembler in order to build object files from YASM. Not a big deal, but one day when we upstream this stuff, we're going to have to figure out how to deal with that, how to deal with an external tool chain, essentially in FreeBSD. So if anyone has any ideas on that, we'd love to talk afterwards. We also did some experiments with reducing the FPU context switches. In order to use AES-NI, it's using the FPU, the SSE blocks. That requires saving the FPU context. And when you're talking about SSE and AVX, you're talking like 512 byte context we saved. We felt that OpenCrypto wasn't doing that very efficiently, so we looked at various ways to basically dedicate CPU cores to doing nothing but encryption. That way we didn't have to worry about saving and releasing context. It could just always be in an FPU context. That led us to thinking about hyperthreading. Normally, we always turn off hyperthreading. It's, for the last 15, 20 years that Intel's been trying to push hyperthreading on the world, it's been a bad idea. It works okay for C++ or Java because C++ and Java are already hugely inefficient pieces of code that have lots of pipeline stalls, and hyperthreading can take advantage of that inefficiency. But when you're talking about kernel code, C code that's generally written fairly tightly, hyperthreading is almost never a win, and usually it's a loss because it just creates more contention on resources, creates more contention in the scheduler. But then we started thinking that, gee, this AES-NI code from ICL or for boring SSL, it's using execution units that normally aren't being used at all. So, normally you have an integer unit, a load store unit, an FPU unit, and a jump unit, a branch unit. And normally, the FPU unit is never used. Well, now we have a use for the FPU unit, and we have code that's highly tuned for it to keep it constantly flowing. So we turned on hyperthreading, and lo and behold, we got a fantastic improvement in performance. So it turns out that doing part of your workload being scalar, integer type stuff going through the kernel and VM system and TCP stack on one side, your hyperthreading core, and then doing AVX, AES-NI type stuff on the other side is a fantastic win. And so we started using our own interfaces to create thread pools that would basically just naturally migrate themselves to being well balanced between the work that was happening in the network stack and the work that was happening in the encryption stack. So then the last thing we did, we started looking at our data paths and looking for bugs that we had, things that we'd missed, things that we could improve to squeeze more performance out that way. We found that when we were still using the OpenCrypto framework that we'd actually accidentally been doing an extra copy of the data, got rid of that. We found that we were misusing when we added, so we were doing the SSL send file as a new system call because we needed extra arguments added to it. And we found that when we migrated our code in Nginx using that system call, we forgot to use some of our flags that we were using previously to control the caching of pages. And in essence, we were crashing the VM system heavily. Everything that we were passing through the system was being cached LRU and then expired LRU, and it was thrashing like it had years prior before we'd done async send file. So we added in the no cache flag, so things would be freed immediately and not thrashed the VM system. And then Randall Stewart, who was the other person who worked on all this, came up with an mbuf vector system for walking mbuf chains. And he calls it mbuf maps. Basically, it's an extra object that hangs off of the mbuf that holds a map of all the pointers to all the other mbufs that are part of that chain. So when you go to walk the mbuf to walk down through the data chain, instead of having to look at the next pointer for the next mbuf and go on to the next pointer, the next pointer, the next pointer, and glue cache lines with just looking at the next pointers to find the next on the chain. Everything gets added into basically into an array, and you can just look at them once, see all your pointers, and then in our case, we were passing those pointers into the encryption routines. So instead of having to walk the chains, as we were building the mbufs, we already had all the pointers in a map, and we were able to pass those off very easily and effectively. His implementation, very, very tiny. I think it's a 128 byte map that can be attached. Comes out of Yuma as part of the mbuf allocation, and it's pointed to from the header, and it can hold up to 10 pointers. For us, since TLS messages are only 16K, we only need to use a few of those pointers, but maybe 10 just in case there will be other consumers of this. And then he created some accessors for it to be able to add and subtract pointers from the map, and then also relinearize the map. So once it got down to the device driver that didn't know about these maps, we need to relinearize everything and add our next pointers along the chains. So it would do that. End result is that it vastly reduced cache thrashing, and a lot of our analysis tools where we look at hot instruction and cache line misses and hot cache lines. It vastly improved that. So all of that taken together, we redid our testing. Where it says OpenSSL userland, that we didn't test the old system that we published last year because OpenSSL, the classic OpenSSL type serving, was close enough to it that we felt that we didn't want to, there was no need to test both that and the in-kernel OpenCrypto. So that's basically collapsed that first row together. But the end result is that on systems where we have 40 gig NIC, and another thing I should explain is that when I talk about like a 36 gigabit max, even though we have a 40 gig NIC, we tend to run our systems at 90%. So 40 gig NIC means that we'll do 36 gigabits max. That way we have a little bit of headroom for packet queuing at the interface without degrading system quality. So with both boring SSL and ISAL with all the other improvements, we were basically able to run at line rate using only half the CPU. Whereas without it, we were not able to get above 30 gigs. We typically try to limit our CPU usage to 80% also, but at a certain point, sometimes we can't even get to full CPU usage because the system becomes so congested that even though the CPU doesn't think it's busy, it's causing so many latency spikes to the clients that they stop coming to us. So, in essence, this was a fantastic improvement all around. It got us from before where on a system that should have been able to do 27 gigs was only getting 8 or 9. Now a system that should be able to do 36, we're getting the full 36 and not even using the full CPU. So future work, the team from Intel that works on ISAL has promised us a new version of the libraries that uses instructions that don't go through the L1, L2 cache. That means that we're not going to be thrashing the cache with all this encrypted and non-encrypted data. We've also been experimenting with some new features from Intel on upcoming versions of CPUs that deal with fine-grained control of caching of pages. That looks like it's giving us a little bit of a result bump. We've also been looking at true hardware offload, things like the Intel Quick Assist and the Cavium Nitrox cards. We have a project going on with Intel right now to bring a modern driver for Quick Assist to FreeBSD. We've just started to evaluate the results from that right now, and it's looking like it holds some promise in certain situations. And then also, as time goes on, we'll have faster CPUs, CPUs with more features, and we'll keep on improving the OS. And the other thing we need to look at is that there's been talk from Google about using the Cha-Cha cipher for streaming video. We don't know a whole lot about that other than they like it because it's a low power. It allows the CPU to operate low power mode on the client, which they like for their tablets and for their phones. But we have no idea what that means on the server side. But the other big thing we have in front of us is that we need to get this code upstream. We've just gotten the async send file code upstream recently. Now we need to get the SSL send file code upstream and all the associated socket buffer changes and infrastructure changes, and like I said, things like ISAL, get that upstream. So that's what we're going to be working on. Goal is to have that done for 11.0, or at least far enough along that it's useful for other people. But like Steve Jobs, there's more. So remember how I said before about we were doing 100 gig line rates unencrypted. Well, we can now do over 60 gigs encrypted on the same interfaces, same CPUs, and we feel that on next generation CPUs we'll probably be able to get between 75 and 80 gigabits per second encrypted. So not quite line rate, but close enough that basically 2x40, you can saturate 2x40 fully encrypted Once again, single FreeBSD server, single socket. We're not using 2 sockets, and all commodity hardware. So when we started, we thought that the penalty for using TLS would be somewhere between 50 and 66% of our CPU cycles. Now it's down to 33%. And probably going to get down to closer to 25%. So that's my talk. Any questions? Yes?
So the code from Intel, they're happy to have that BSD license?
Yes.
Awesome.
Yes, they're just looking for someone to upstream it for them. And like I said, they have code that covers zlib and SHA and a whole bunch of other things too. So we're only interested in the GCM stuff for now, but you know, when it comes time to upstream, there's the infrastructure to put into the kernel and user land. We'll look at putting it all in. Yes.
In that last slide where you're at 60,
yeah.
Are you just saturation?
Yeah, at that point, the CPU is about 85%, so we're actually cheating a little bit above our normal 80% target. But that's part of some of the other performance work we're doing is that we've always picked an 80% target because we always have parallel processes that are starting and stopping for doing housekeeping and stats, and you know, occasionally there's spikes because we have rush traffic or whatnot. We're actually working on trying to flatten those spikes now so we can run our CPUs closer to 90% rather than only 80%. So that's why we don't feel too bad about saying that we're at 85% CPU now, because that's, you know, that's part of our target. Alan?
Do you use accept filters at all?
We don't. Our connection rate is only like 10 connections per second. So that's why we can afford to do the handshaking and key exchange in user land, because it's such a low rate, and accept filters. We thought about it, it just never made any sense. Yeah.
So it would be fair to say you guys are probably responsible for most of the SSL traffic.
That I'm waiting for Sandvine to start talking about that.
Given that, are you guys using perfect full secrecy for in your services?
I don't know what that is.
Okay, so the idea is that you basically make it, every session has an ephemeral key.
Okay.
So that it's not possible to derive what the...
Oh, yeah, so, and Alistair just is sitting there nodding, yes we do.
Oh, okay. Okay, very good, because that would make things harder to the NSA.
All right.
Without it, if they got your private key, they could decrypt all traffic that had ever been encrypted by your server. Right.
So how much of your traffic is TLS?
I think it's between 20 and 30%, maybe a little more. Like I said, we've been ramping up more and more classes of clients. I think the goal is by the end of this year is to be as close to 100% as we can be.
And if the client has to come in and ask for it?
So all clients that are capable of doing it will be given. So when when you hit play on a client, the client talks to AWS, negotiates keys, and gets a list of URLs that represent the files it wants, and some of those URLs will be HTTPS if the client is capable of them. Yes? So for AWS, like I said, that's all of our back-end logic and infrastructure. That's actually running Linux, Ubuntu, I think. And really, it's all Java platform type of stuff. So we don't have any FreeBSD running there, other than I think we have a few instances running here and there for doing build farms, that kind of thing. But
so you just using Amazon's EC2 service and just running on FreeBSD virtual machine.
no. So for the serving, it's all of our own hardware. It's not part of AWS. And then for the part of the company that is AWS, that's all Linux. There's no virtual machines. On our own hardware, it's all bare metal. We're not using any kind of virtualization on our OpenConnect hardware. Yes?
Have you thought about using Nmap in order to avoid placing all these things inside of the kernel?
We thought about that initially. We already had the data pass through the kernel that was working well. once we solve some VM issues. The problem with using nmap is that then we have to put our storage stack into userland also. And while it was possible to get a userland TCP stack and do caching userland, the storage side was going to be a very heavy lift for us.
The penalty of sending, of moving this data from the kernel space to the user space, it's too high for you, basically, I guess.
Yeah, we thought about, we could do nmap regions and shared memory regions that way, but this was working. All right, anything else? Come on, Phil, I'm sure you have a question.
Oh, I have a question.
All right, well, thank you very much.